Hello friends, welcome back to my channel, and in this video we will solve a problem in the concept of random processes. It is about passing a White and stationary random process through an LTA system, specifically an RC low pass filter. So we take the output across the capacitor. The problem statement goes like this. Consider the RC circuit as shown. Let the input be a White and stationary random process. The output also will be a White and stationary process. Let the input be W of t and the output be N of t. If the input has a zero mean and if its power spectral density is N naught by 2, we have to evaluate these terms. What are they? First one, we have to evaluate the mean of the output process. We have to evaluate the power spectral density of the output process. And based on this, we have to find the variance of a random variable N of tk, where N of tk is a random variable obtained by sampling the random process N of t at tk. So let us jump into the solution. So we have again the our low pass RC circuit, and the output is taken across the capacitor. So very first step in the solution is to evaluate the power, evaluate the frequency response of this RC filter, and that would be given by h of f is equal to 1 by 2 pi fc divided by r plus 1 by j2 pi fc, and after simplification that would be equal to 1 by 1 plus j2 pi f rc. Okay, and now let us look at the generic results of a basic LTA system. So we have an LTA system for which x of t is the input and y of t is the output, and the input is a White and stationary random process, by which we mean the mean of the random process is constant, which is equal to mu x, and it has autocorrelation function Rx of tau, and hence its power spectral density is Sx of f. So if you take the Fourier transform of the autocorrelation function, we get the power spectral density of the random process. And the properties of the LTA system would be, we have the impulse response h of t and the corresponding frequency response h of f, which is nothing but the Fourier transform of the impulse response h of t. So, and the output y of t is also a White and stationary random process with a constant mean of mu y, which we have to evaluate, and the autocorrelation function of ry of tau, which we will see, and also the power spectral density sy of f. Okay, yes, so this information is given to us. The output random process y of t will have a mean mu y, which is given by mu x into h of 0. So this is a well established result and we are not going to prove this. Okay, and here h of 0 is the evaluation of the frequency response of the LTA system at f is equal to 0. Similarly, ry of tau, which is autocorrelation function of the output process y of t, is nothing but rx of tau convolved with h of tau convolved with h of minus tau. So note that h of tau and h of minus tau is nothing but the autocorrelation function of the impulse response of the system, of the LTA system. Okay, and hence what is that you observe? You observe that the output random process phi of t, it has an autocorrelation function which is given by the autocorrelation function of the input process convolved with autocorrelation function of the LTA system. We can see this equation in that fashion. Now if you take the Fourier transform of this Ry of tau, we get the power spectral density, and we know that for convolution in time domain corresponds to multiplication in frequency domain, and hence Rx of tau will have Sx of f as the power spectral density, and h of tau has h of f as the frequency response, and h of minus tau will have h of minus f as a frequency response. This comes from the property of time reversal. Now let us go back to the problem. Here we have an RC circuit and it is an LTA system, and hence we can apply the results what we saw in the previous slide. So very first problem is to evaluate the mean of the output process, which is nothing but expectation of n of t. So we know the result. We already saw the result that mu n would be equal to mu w times h of 0. So let us, and we know that h of f is given by 1 by 1 plus j2 pi f rc. Now mu w, we already have that to be 0. So substituting both of them, we get mu w is 0, and h of 0 you get by substituting f with 0. You get 1 by 1 plus j times 0, which is equal to 0, and overall result will give you mu n to be equal to 0. So what is the mean of the output process? That is equal to 0. So what is the second question? Second question is to evaluate the power spectral density of the output process. So we already got the result, which is given by power spectral density of the output process is nothing but power spectral density of the input process multiplied with frequency response of the LTA system and the frequency reversal of the frequ- uh, f- frequ- uh, frequency reversal of the frequency reversal of the frequency response of the LTA system. Yeah, sorry for that. Yes. So yes, so this is what we have to find out, right? So, but we know the SW of F, which is the frequency response of the input system, which is nothing but N naught by 2, and H of F, we calculated that to be 1 by 1 plus J2 pi F RC, and let us substitute that. So, what do we get? SW of F is N naught by 2, H of F is 1 by 1 plus J2 pi F RC, and H of minus F is 1 by 1 minus J2 pi F RC. How do you get this? By replacing F with minus f. So this simplifies to what? N naught by 2 multiplied with, so here the denominators are complex conjugate terms, and hence if you multiply you get 1 by, total term would be 1 by 1 plus 4 pi square f square r square c square. Okay, so that is what we have got. Now the next, that is the second question, right? So we have to evaluate the frequency response of the output process, and we got this. Now third question is, if you sample n of t at tk, so what is the variance of the random variable n of tk? So that is what we have to evaluate. Note that if you sample a random process at any instant of time, we get a random variable, and the question is we have to find the variance of that random variable. So let us try to solve that. Yes, so we got the power spectral density to be n naught by 2 times 1 by 1 plus 4 pi square f square r square c square, and now we have to evaluate the variance of n of tk. So n of tk is a random variable. So by using the regular definition of the variance, we get variance of n of tk to be expectation of n square of tk minus expectation of n of tk whole square. Okay, and we already know that expectation of n of t is 0, and hence expectation of n of tk also would be equal to 0, and hence this expression simplifies to what? Expectation of n square of t square. So this is nothing but autocorrelation function evaluated at tau is equal to 0. But by using the Fourier transform properties, we can easily see that Rn of 0 is nothing but the area of the power spectral density. So these are the already well established results, and we are not going to look at how these are correct. Okay, they are proved, and hence we will take the result. So I will defer the discussion of the proof of all these results to some other lecture. Okay, right, now let us go back to the problem. So what is that? We are asked to evaluate the variance of n of tk, and we got that to be equal to what? The area of the power spectral density Sn of f. So we already got Sn of f here, so let us substitute and see what happens. Yes, so that should be equal to integral minus infinity to infinity n naught by 2 times 1 by 1 plus 4 pi square f square r square c square times df. Okay, so we can take a naught by 2 out, and finally we get this integral. But how do you evaluate this integral? So there is well established identity in the integral equations, and that is given by integral minus infinity to infinity 1 by 1 plus a square x square dx is equal to pi by a. So this is easy to prove, but we are not doing that. So let us apply the same result here. So look at this integral and look at this integral. They're almost same except that, so instead of x we have f here, instead of a we have 2 pi rc. Okay, so you can easily correlate with that, and hence we can evaluate this integral to be n naught by 2 times pi by a, I already told that it is 2 pi rc, and by cancelling the common term, that is pi, we get n naught by 4 rc, and this is the variance of the random variable n of tk. So with that, I will close this video. And what is that we have seen? So we are asked to evaluate the mean of the output process, we are asked to evaluate the power spectral density of the output process, and we are asked to evaluate the variance of the random variable obtained by sampling the output process, and that we have evaluated. Hope you have understood the concept of wide sense stationary random process through an LTA system. Thank you.